Swayam Prabha. Digital India. Educated India.
Welcome to the NPL course on Advanced Ceramics for Strategic Applications. This is H.S. Maiti welcoming you to this particular course. To start with, we will discuss some introductory concepts about ceramics, their properties, their characteristics. Then we will come to the different classes of ceramics, different materials available to us, and also the major raw materials from which these materials are prepared. And finally, we will discuss some of the basic principles of manufacturing techniques of these ceramics. What are ceramics? Well, how do we define ceramics? Maybe it is known to many people that this particular name ceramics came from a Greek word keramikos, which basically means burnt material or burnt stuff. As it is known, the ceramics are known to mankind for thousands of centuries, and they are basically prepared from naturally occurring raw materials. They are normally inorganic and non-metallic materials having relatively high melting points, and therefore requires high temperature for their processing and fabrication. So, that is how normally we define ceramics. They are usually compounds, not the elements, but the compounds of different elements or combination of compounds between metallic as well as non-metallic elements. What are the elements present in different kind of ceramics? Of course, they are metals in addition to oxygen, nitrogen, carbon and boron, maybe some others. The examples may be very simple example, a very common example is aluminum oxide. It is a mixture or it is a compound of aluminum and oxygen. Another example of ceramics is a combination of two oxides or compounds of two different oxides like aluminum oxide and silica or silicon dioxide in a particular ratio 3:2, and that particular compound is called mullite. Well, to continue, what are ceramics? We also have, in addition to oxides, we have carbides, nitrides, borides and silicides. That means a combination of metal with carbon, a combination of metal with nitrogen, a combination of some metal with boron and also silicon. So, these are more different or uncommon type of compounds which are available under the category of ceramics. They are always composed of more than one element, as has already been said, and few other examples are silicon dioxide, zirconium dioxide, magnesium oxide, silicon carbide, that is one kind of carbide, a combination of silicon and carbon. Then you have silicon nitride, a combination of silicon and nitrogen. Well, any compound has certain category or certain classes of atomic bondings, because we are dealing with two different elements, and as is known from our chemistry knowledge, some of these compounds are ionic in character, the bond is ionic in character, and some others are covalent and so on. When we talk about ceramic materials in general, we have variety of bonds. Some of them, particularly the oxides, are totally ionic in character, whereas if you talk about carbides, nitrides, borides and silicides, they have partially ionic conductivity, ionic bonding, whereas mostly they are covalent bonds, or covalency is the character of these bonds. Well, what are the different general characteristics of ceramic materials? We have seen there are oxides, carbides, nitrides, silicides. Can they have some common features? The most important characteristics of any ceramic material that it is brittle. It does not have the necessary plasticity like metals or other plastic materials. So, it cannot be extended, or it can be deformed, it cannot be deformed. The deformation is very little before it breaks. So, that is the characteristics of brittleness, and all ceramic materials have this particular property. Then you have another very important property. In general, most of the ceramics are chemically inert. They do not react with other chemicals or environment, and therefore, they are quite stable, chemically very stable materials mostly. They have long life, they are durable for a long time. So, that is another good advantage so far as the ceramic materials are concerned. In addition, they have very high strength. Of course, when you talk about strength, we have to define what kind of strength it is. Ceramics are very strong when a compressive load is applied. However, if you apply a bending load or a tensile load, they are quite weak. So, unlike metals or even polymers, ceramics have this kind of weakness, although they are very strong under compressive load, but they cannot be bent. Then the brittleness comes in. In addition, they are hard and therefore wear resistance or abrasion resistance. They can be abraded, or they cannot be abraded, they can abrade other materials. Normally, they are electrically as well as thermally insulating, that means the electrical conductivity is very poor, as also the thermal conductivity. Refractory nature means it is basically high temperature resistance. As per definition, ceramics are high melting materials and requires high temperature for their processing, and therefore, refractories are the most common candidate material to be used as a refractory material for lining of furnaces, particularly where a very high temperature has to be withstood. Chemically stable, as you have already mentioned, then and that is why they are durable also. And so far as the magnetic properties are concerned, most ceramic materials are not magnetic, but there are exceptions. These properties are however not common to all ceramics. In fact, ceramics as a group has the widest variety of different physical and chemical properties. We will discuss them, what are the different extreme properties. Sometimes ceramics are insulating as I have just mentioned, but not necessarily all the time. There are groups of ceramics which are semiconducting, others are conducting almost like metals, and then few decades back, about 2-3 decades back, we have also got a completely new range of ceramics which are superconducting. So, ceramics as a group has a very widest spectrum of different physical and chemical properties, and that will be discussed in next classes. Some exceptions we have just discussed, what are the common features or common characteristics of the ceramics as a group, but there are many exceptions. As I have just mentioned also, superconductor, there is a compound, an oxide of yttrium, barium and copper which shows superconductivity, and this is a very recent discovery. Although we have said most of the ceramics are not magnetic, but there are magnetic ceramics as well, and this is one some example. It is a oxide of barium or strontium along with iron oxide, which is called barium ferrite or barium hexaferrite, and that is a hard magnet. Once you magnetize them, it forms a permanent magnet. In terms of mechanical properties, although most of the ceramics are brittle, but there are tough ceramics also, and one of the examples, there are many tough ceramics have been discovered in recent times. One of the examples is what we call partially stabilized zirconia, zirconium oxide or zirconium dioxide, to which some amount of yttrium oxide or calcium oxide is added. It is basically a solid solution. It is called partially stabilized because it has a combination of monoclinic or tetragonal and cubic phases. Therefore, it is not fully stabilized. In the fully stabilized condition, it is completely cubic phase or cubic structure, whereas when it is partially cubic and partially tetragonal or monoclinic, then it is called partially stabilized zirconia. So, that is one of the tough material. Of course, compared to steel, it is much less tough, but compared to many other ceramics, it is much tougher. We will discuss them later on. Then you have new high performance ceramics which demonstrate unusual properties, as for example, high toughness, high conductivity, which I have mentioned a few minutes back. So, you have a range of oxides or ceramics which are tougher in mechanical property terms, and the electrical properties are also very different from other ceramics. So, we need to understand, there is a need how these properties really get developed, what is its origin, and therefore, we need to understand a structure property relationship. In material science, the basic subject of material science, in which ceramics is one of the components, if you want to understand the properties, whether it is mechanical properties, electrical properties, magnetic properties, dielectric properties, all these things originates from its structural characteristics, atomistic structural character, crystal structure characteristics. Both crystal structure, microstructures, everything are important to understand if we want to explain some of the properties which we exploit in practical sense. So, having known that there are variety of properties, variety of materials from the chemical or the bonding point of view, we must know how to classify them. Can we categorize them under different groups? Yes, we can certainly categorize them under different groups. So, ceramic material as a whole can be grouped under two important subgroups. What is called, the one group is called traditional ceramics, the other is called advanced ceramics. This course is particularly on advanced ceramics. So, most of the time we will spend on advanced ceramics. However, we must differentiate, we must be able to differentiate what is the, how it is advanced, advanced relative to what. In fact, advanced related to traditional ceramics. So, we must know what is traditional ceramics and also how to differentiate the advanced ceramics from the traditional ceramics. So, let us look at it. We classify traditional ceramics again under different heads like red clay products, white clay products, refractories, then you have cements and also abrasives. These kind of applications have been known for a long time, particularly red clay products, because many of them, particularly red clay as well as white clay, they use the most crude form of raw materials which are available in nature. For example, red clay products, they are basically ordinary clay available in nature at different parts of this earth's crust or earth's surface. We will discuss in a few minutes how exactly the ceramics are prepared. Ceramics are basically starting materials are powders and they get consolidated, and then one of the major steps of bringing in strength to ceramic materials is what we call firing or heating to high temperature. So, this red clay, the common clay, when you heat to high temperature, maybe about 800 to 1000 degrees centigrade, they convert to a strong body having a red color, and this red color basically comes from iron oxide. So, the clay which is normally available contains a lot of iron oxide, and when it is fired it produces the brick, what you call the brick red color. So, all the products prepared from normal clay or common clay are known as red clay products because of the red color, and there is the most crude way of ceramics, although they are known for a long time, but they are the most crude way of ceramics, and they have many different forms. One we call stoneware, then we call earthenware, building bricks, normal building bricks from which the color claims the brick red color, and then terracotta, the figurine, the different artwork, all these things can be made from the common clay. So, they are grouped under red clay products. However, there is another variety of clay which are relatively pure form of clay, which does not contain that much of iron oxide, and their particular mineral, the kaolin or kaolinite, is the major component of white clay, again available in nature as a raw material, as a mineral, and that can be directly taken from the mines and process it little bit and then give it a shape and fire it once again above slightly above 1000 degrees centigrade, so that you get a range of different products which have been known to the mankind for a long time. And they are all called white clay products because their color is white. They of course can be colored by addition of control amount of coloring elements, but in general they are white in color, and therefore, sometimes the whiteness itself is an attractive feature of these products, for example, in crockery or in tiles, sanitary wares, electrical insulators. Of course, the electrical insulators are not white in color, as all of us know. Electrical insulators are brown in color, and they have been intentionally colored by addition of certain oxides again. So, these materials, the basic raw material, are white clay products, or in other words sometimes we call them porcelain products. We will find what are the different components of this white clay products or porcelain products, sometimes called white wares. Sometimes they are also called triaxial porcelain because they require 3 different ingredients. We will discuss that later. So, in addition to red clay products, you have white clay products. Then there are others which are used for high temperature applications called refractories, and once again they will have several subgroups depending on at what temperature they can be used, what is their melting point or softening point. Fire clay is another kind of clay, once again available in nature or in the form of a mineral, and that mineral can be directly fired to high temperature and form a sap. So, it has some amount of aluminum oxide and some amount of silicon dioxide that forms fire clay. In fact, ceramics have been classified in terms of their alumina content, alumina or aluminum oxide. Aluminum oxide, the content of aluminum oxide actually determines the temperature up to which it can be used. Higher is the aluminum oxide content, higher is the temperature it can resist, and therefore, the temperature or in refractory terminology it is called refractoriness. The refractoriness of high alumina refractory is more than that of fire clay refractory. In addition, the another oxide again which is available in nature, magnesium oxide. In fact, magnesium oxide is not as such available, it is magnesium carbonate which can be calcined or heated to high temperature to form magnesium oxide, and that magnesium oxide is also a very good refractory material extensively used for steel making. So, these are the different varieties of refractories which has been known to mankind for quite some time. Then we have another group of traditional ceramics which has been known once again to the human beings for a long time, and as you know, cements is one of the most important building materials used today for all kinds of structural applications, whether it is building, bridge, roads. Cement is another very important group of ceramics which is used, and one of the highest tonnage materials produced across the world. It is basically a combination of calcium oxide, silica and aluminum oxide, and it forms what they call a pozzolanic compound or pozzolanic property. It develops a pozzolanic property, so that when it reacts with water it forms a hard mass. So, it is a cementitious property is develops just by adding water to it. Of course, it needs high temperature for its preparation. just by mixing aluminum oxide silica or silicon dioxide and calcium oxide will not form cement. It has to be fired, it has to be heated to a very high temperature of let us say 1600 degrees centigrade. So, that is another variety of traditional ceramics which has been known for quite some time. Others, the last one in this group is abrasives, primarily because ceramics in general are hard. So, it can scratch any other surface, particularly the metal surfaces. Any metal surfaces can be scratched by a ceramics. Of course, there are different varieties of ceramics, some of them are little softer than the others. So, in case of ceramics or the abrasives, we use the harder variety of ceramics. So, these are the groups of traditional ceramics and the different kind of raw materials or the compounds we use. The next group, which is basically the topic of this particular course, is advanced ceramics. Now, what are these advanced ceramics and why they are called advanced ceramics? There are two subclasses of advanced ceramics. One is we call it electroceramics, the other is structural ceramics. As the name suggests, the electroceramics actually deals with the electrical properties. There are variety of electrical properties, as I mentioned few minutes back. So, we need or there are large variety of properties which can be exploited for industrial purposes or application point of view, and those things where electrical properties is the primary properties which is exploited, they are called electroceramics. And under that group you have various applications areas, various properties as well as their application areas. For example, you have electronic substrate and packages. These are basically insulating material, pure oxides, and they can be formed in thin sheets form or different other fabrication techniques can be used to form different shapes. We will discuss them at a later stage. So, but basically in the electronics industry you need many insulating oxides, particularly aluminum oxide is one of them. There may be some nitrides also which can be used, but they exploit or in those applications we really exploit their insulating property. Then you have dielectric properties. Ceramic dielectrics. The insulatants, insulating materials also have a good capacitive or dielectric constant, and therefore, some of these oxides can be used as miniature capacitors, particularly used in electronics industry. Many of these dielectrics once again have a very special property called piezoelectric property. Piezoelectric property is that property in which you can develop certain voltage by applying a mechanical stress. So, if you stress them, if you apply some mechanical stress, it generates some voltage. There are many oxides or mixed oxides which develop these properties, and they have been extensively used in the electronics industry for many different purposes. We will discuss them at a later stage, but this is another very important group under ceramics where piezoelectric and dielectric properties has been exploited to develop different devices and functional materials. Then you have another group called magnetic ceramics. Although most of the ceramics are not magnetic, but there is a special group of ceramics which are actually have a very interesting magnetic property, and they are comparable with the normal metallic magnets like iron, cobalt, nickel, okay. And they can be used both as a temporary magnet or electromagnet, also as a permanent magnet. One example I have shown you little bit few minutes back is barium ferrite or strontium ferrite, which actually has a permanent magnetic property. So, there is a group of magnetic oxides also present or available to us. You have then another conducting ceramics. These are, we have discussed insulating ceramics here, then we have magnetic ceramics, and then conducting ceramics. They can be semiconductors, they can be conductors or even superconductors. So, there are very basic science have to be understood, how, or the physics have to be understood why these ceramics or these compounds behave in this manner. So, there is a gamut of many different compounds which have this conducting property. So, they can be classified or grouped as conducting ceramics. The last one in this series is optical ceramics. Although ceramics are in general opaque, okay, light cannot pass through them. However, under special circumstances, if you can fabricate or process them in a special way, then ceramics can also be made transparent, almost like glass. These are optical ceramics is not glass. Glass is a different class we are not discussing here, but some of these oxides can also be transformed into a transparent material. By heating at high temperature under special conditions, one can make absolutely transparent ceramics like glass, but they are crystalline materials and they have many different or special properties which you can exploit for different device making. For example, electro-optic materials or optoelectronic materials can be developed, and there are many different things. So, we will discuss these things under the advanced ceramics group of materials. Besides electroceramics, you have another very important group where you actually use the mechanical property or mechanical behavior of these ceramics, and that is why they are called structural ceramics. So, it is a mechanical property which becomes important here, and they also can be classified under different groups like automotive ceramics. Well, automotive engine is primarily, as we know of, primarily made of metallic materials, different kind of alloys, because it has to withstand a very high pressure as well as very high temperature because of the combustion of the fuel. But ceramics can replace some of the metallic components in this case. One of the advantage of ceramics is it can withstand high temperature, and therefore, much better than metallic materials, and therefore, it has an advantage, it has an edge over the metallic materials. In addition, under compressive load they can also withstand very high pressure or very high stress, mechanical stress. So, some of the components of the automotive sector can be replaced and has been replaced by ceramics, particularly by some of the top ceramics. And the advantage is you can operate the auto engine at a relatively high temperature. And it is also known from thermodynamics that if you operate a Carnot engine at a high temperature, its efficiency goes up. So, that is the driving force, that is the attractive feature of ceramics. By using some auto components, particularly the engine block, you can raise the temperature of operation of an automotive engine and thereby have or get a much higher efficiency. So, actually it helps in two ways: it consumes less fuel and less pollution. So, ceramics has a great advantage if you can use them under high temperature conditions and high pressure conditions. The other group, next group is aerospace, is almost an extension of the automotive sector. You can have turbine blades in the aerospace or aero engines. The turbine blades are normally made of very high quality metallic alloys, but it has its own limitation so far as the temperature of operation is concerned. If you can coat them with the ceramics which can resist much higher temperature, you can operate a gas turbine at a much higher temperature and therefore get high efficiency and less fuel consumption. So, this is one again another attractive feature of ceramics, where you can use them at very stringent under very stringent conditions, high pressure conditions and as well as high gas velocity conditions as well as high temperature conditions. So, these are where it is the these are the areas where you actually exploit the high temperature and high strength condition or thermomechanical properties of ceramics to generate a better or more efficient engines. Because of the hardness, we knew about abrasion resistance, but then it has been extensively used these days for many wear resistant ceramics, maybe ceramic different kind of ceramic coatings. When you talk about abrasives in the on the traditional ceramics head, it was actually normally the grains of ceramics, but here the wear resistant ceramics is actually either a lining on a metal surface or a coating on metal surface, a thin coating on metal surface. So, these are being used more extensively in high application areas. As wear resistance coatings or sometimes as tiles. Then you have cutting tools. Once again, the high temperature and high strength property, the thermomechanical property of ceramic compounds or ceramic materials are exploited in making high performance cutting tools, high speed cutting tools, because it generates at the cutting tip, it generates very high temperatures. When you are trying to cut metals or turn metals with some cutting tools, ceramics is a much better option than the normal tool steels. Okay. So, it needs high temperature and high hardness, okay, at high temperature, high hardness, and that can only be provided by cutting ceramic materials. So, cutting tool application has become again a very important application for structural ceramics. And finally, a completely new area of ceramics has come up once again in the last couple of decades or 2-3 decades. This is called bioceramics, biomedical implants. Okay. In our body, we have bones, and those bones are basically one of the components of those bones are ceramic materials, hydrated calcium phosphate, or sometimes it is called hydroxyapatite. So, these bones contains lot of ceramic materials or compounds, and that can be artificially made outside the human body and can be replaced. If there is a fracture in some of the bones, in some of the joints in particular, either knee joint or a hip joint. So, they are actually the load carrying capacity, load carrying points or the joints of the human body, and you can replace them. You can replace them with ceramic, with fabricated ceramic steps, and therefore, there is a huge potential of ceramics being used as biomedical implants, and it is really being used these days. In addition, there are many other ceramics which can also can be used for biomedical purposes. And therefore, that group of ceramics, of course, it not only uses the mechanical property, high strength of the materials or high hardness of the material, abrasion resistance property of the material, but also it needs different kind of chemical inertness as well as sometimes it reactivity with the body fluid. So, ceramics is inert so far as the body fluid is concerned, and therefore, ceramics, a group of ceramics has come up in very recent years as bioceramics. So, there are a whole lot of ceramic materials available to us whose properties were not known earlier. Maybe 50 years back we are not knowing many of these properties of these oxides and carbides or nitrides, but now we have understood many different properties and naturally more and more application areas are coming up. So, that actually forms the so called advanced ceramics, okay, which is quite different from the traditional ceramics which we have discussed few minutes back. Well, to start with the different classifications, as I mentioned earlier, there are oxides, there are carbides, there are nitrides, all of them are grouped together under ceramics. So, among the oxide ceramics, we have earlier mentioned, once again I am re-emphasizing that there are aluminum oxide, there are magnesium oxide, there are zirconium dioxide. These are simple oxides where only one particular metal is involved along with oxygen, whereas there are complex oxides or mixed oxides, sometimes they are also referred to as mixed oxides, like aluminum and titanium forms aluminum titanate. Then there is a mixed oxide or a solid solution of lead oxide, zirconium dioxide and titanium dioxide, which called lead zirconate titanate, sometimes in brief it is called PZT. You have silicate ceramics. Silicates are basically used in traditional ceramics, most of the silicates, because they are naturally occurring, some of these silicates are naturally occurring, and porcelain is one of the areas where silicates are very much extensively used. But in addition, you have more purer variety of oxides like magnesium silicate or 3Al2O3 2SiO2, it is a mixed oxide of aluminum oxide and silicon dioxide, and a particular compound or particular mineral is called mullite. These have different properties. Once again, they can be used as a refractory material, high strength or high performance refractory, or these are possible it can be used in some of the insulating components. Well, besides oxides you have carbides and nitrides, and there are many different carbides, some of them have been already discussed. So, here is boron carbide, one of the hardest material next to diamond. Okay. The boron carbide is one of the hardest material next to diamond, and it is an industrial product. Silicon carbide is extensively used as a structural material or structural ceramics, and then you have tungsten carbide, which has been known for quite some time, but it has also can be grouped under ceramics because it is basically a carbide. These carbides are tungsten carbide been used as cutting tools for a long time, but today some of the tungsten carbide has been used by or replaced by other more advanced ceramics like silicon aluminum oxynitride or even silicon nitride and so on. Well, ceramics in general are porous, because the basic raw material from which most of the ceramics are prepared are powders. So, powders gets consolidated and then are given a shape, geometric shape, and then you actually fire them or sinter them at a higher temperature when the mechanical strength increases, but all the pores, the interparticle porosity or openness do not get completely sealed. So, you do not get a completely dense ceramics all the time. You need special attention to make completely dense materials, but in general you start with porous materials. So, ceramics are in general porous. We will see at a later stage how this porosity can also be utilized for many different industrial applications, but generally porous or the general tendency is to reduce the porosity. Sorry. So, you have open pores. Okay. In silicon carbide you can have open pores, and these pores sometimes have to be sealed, or you have to make a dense material, and for that there are different techniques, like you add some additional material. So, you have silicate bonded silicon carbide, recrystallized silicon carbide and nitride bonded silicon carbide. In most of the ceramics, many a times you use some bonding material, because bonding is always difficult in ceramics, because particles or fine powders have to be bonded together, so that you get a strong material. So, these are different kind of bonding mechanisms or bonding philosophy by which one can make a dense material. These are silicon bonded silicon carbide, silicate bonded. Then you have recrystallized, that means you heat it to very high temperature, so that you do not need any other bonding, but they themselves bond together. That is what you call recrystallized silicon carbide. Sometimes nitride, silicon nitride is added as a bonding material. So, these are variety of different products one can make from the basic material of silicon carbide. On the other hand, you have dense silicon carbide, where a liquid phase has been added, some dopants have been used, different oxides been used, they form a liquid phase at a very high temperature and then fill up the pores, and that is why you get a dense material. Sintered silicon carbide is once again you at a very high temperature, just like recrystallized silicon carbide. This is also a high temperature sintered silicon carbide. Silicon infiltrated silicon carbide, that means at a high temperature silicon melts and then fill up the pores in between the interparticular space. Interparticle spacings can be filled up with silicon metal, and that is silicon infiltrated silicon carbide. Hot pressed or hot isostatically pressed. Well, normally ceramics are initially pressed at a or given a shape or consolidated at a room temperature and then heated. But in this particular case, this is a variety of material. There is a particular type of material in which material is pressed or consolidated and heated simultaneously, and therefore, you can get a much finer grain material, and this material has a much better mechanical property than the normally porous materials. So, there are different techniques of making the same material in the different microstructure with different microstructures or different state of consolidation, and accordingly developed different mechanical properties. So, microstructure is a very important aspect of preparing or developing structural ceramics. We will discuss them again in greater details at a later stage. Nitride ceramics, we have discussed oxides, we have discussed carbides, and these are the few examples of nitride ceramics. The simple one is the silicon nitride, and then you have oxynitrides. So, it is a combination of silicon, aluminum and oxygen, okay. Or you can have aluminum nitride. So, these are all different covalently bonded materials and having a very high strength as well as high temperature property. So, there are nitrides of different types, we will take examples of that at a later stage. Well, we have just given you some idea what is the so called traditional ceramics, that means ceramic materials which have been known for a quite long time, and then we are beginning to know more different kind of materials, more purer variety of materials, different kind of compounds which are having a different exotic properties, whether it is mechanical property, whether it is electrical property or so on. So, you have a group of materials which are being developed or coming up as having many exotic properties. Obviously, these exotic properties can be exploited for our benefit, for our industry's purposes and so on. So, there is a clear distinction between one group of traditional ceramics, where the raw materials are primarily clay based products or the natural raw material, naturally occurring raw materials, whereas there is another group of materials, pure oxides, synthesized compounds like nitrides, carbides, they are not available in nature as such. So, you have to take purer variety of materials and then synthesize under the laboratory condition or the industrial conditions and develop different properties. So, we will not be discussing in this course about the traditional materials anymore, but we will focus our attention to the exotic materials, specially prepared materials, so that you can develop a unknown properties and exploit them for our benefit. So, there is a development which is taking place over centuries, right, and this is the kind of graph one can plot. You can say, so far as the material use is concerned, the whole spectrum of the centuries can be divided in different parts. We started with Stone Age, then came pottery or white wares, then came metallic materials, when we learned how to extract metal from the minerals. One came from Copper Age, where the bronze came in, it is an alloy of copper and zinc, and then came the Iron Age, when we understood mankind came to know how to extract iron. It is one of the largest or tonnage materials, tonnage wise the largest group of materials produced by mankind and used for different structural applications. So, this is how it got developed over the centuries. These are all before Christ, BC. And then there is a lull period, not much of development took place so far as the new materials are concerned. Then of course, after iron one could find out the advantageous properties of steel, and then suddenly there is a extensive development or extensive knowledge so far as the new materials are concerned. We could understand the property of semiconducting property of silicon. Then we also came to know about the polymers, which are a group of materials itself, and then photonic materials. Photonic materials are basically like optical fibers, they are basically glass fibers. Okay. So, glass were known, but the basic property or the development of glass fiber became known only about 40-50 years back. Then you have advanced materials, some of them, all of them are not ceramic materials, some of them are composite materials, ceramics, metals, metal composites, and then as I mentioned biomaterials. Biomaterials also includes, I gave the example in context of the ceramics, but ceramic materials are not the only materials which can be used as biomaterials. Biomaterials can contain metals, polymers, composites and so on and so forth. So, this steep rise is coming up and is continuing now with the explosion of knowledge, the explosion of scientific knowledge which we have been generating over the few decades. So, this is the era where advanced materials have come in and advanced ceramics is one component of that. If you take this graph, you will see the natural materials like wood, the use of wood is going down, in fact to some extent intentionally because of the environmental issues. Steel have been started couple of centuries back, and then you have an increase in their use, but around 1987, 80s or 90s it got a peak and currently it is dropping. So, the use of steel is dropping so far as the structural materials are concerned. Some of it is getting replaced by plastics, but many of them are getting replaced by composites and ceramics. So, ceramics has not been specifically mentioned here, but these advanced materials actually constitute a major component is ceramic materials, right. So, the use of advanced ceramics is increasing and it is expected to increase for quite some time now. As you can see, this graph has been extended beyond 2050. Well, now we come to the raw materials. The raw materials for the traditional ceramics, because we have discussed about the traditional ceramics and advanced ceramics, and we have to try to differentiate from the property point of view, but there is a strong dependent on the raw materials used for this. Okay. And there are different components of raw material, particularly in traditional ceramics. As I mentioned some time back, there are, we call sometimes that triaxial porcelain, because there are 3 different components of this composition. Okay. One is plastic material and there is fluxes, there are different purposes for which they are used, and then you have fillers, or which provides the basic mechanical strength to the body, ceramic body. Okay. So, these are 3 components of the whiteware body or the traditional ceramic material. One is the plastic material, another is the flux, and there is fillers. So, the plastic material is basically clay or talc, is another silicate, basically magnesium silicate, hydrated magnesium silicate, and then you have feldspar, that is again another mineral which used as a flux because it melts at a lower temperature, and then we have some non-fluxing materials like quartz. Okay. So, these are the 3 components normally used as a raw material for the traditional ceramics, and they are all naturally occurring. It needs little bit of mineral beneficiation and then can be directly used for the product fabrication, whether it is crockery, whether it is tiles or sanitary wares and so on. So, with this we close this lecture so far as the traditional ceramics is concerned. In the next lecture we will see what are the different raw materials used for advanced ceramics, and then what are the different common ceramic processing techniques which give rise to the product formation or the product development. Thank you.